Hi all, welcome to the lecture series on Aerospace Propulsion. This is Manideep Gupta, Assistant Professor from MLR Institute of Technology. Today the topic which we are going to discuss is energy requirements for an orbit. So if you want to send any satellite from Earth surface to the orbit, we need to provide some enough energy for the body so that that body will enter into the orbit. That means it will reach to the orbit. After that, it will rotate with certain velocity so that it will stay in the same required orbit. So, today we are going to discuss about all these energy requirements. What energy need to be provided for the object to reach the orbit, after that to rotate in the same particular orbit. Coming to the overview of today's presentation. So, in the today's presentation, we are going to discuss the energy requirements to reach a orbit. First thing is energy requirement to reach a orbit. Next, total energy required to rotate in the orbit and velocity required to rotate in the orbit. So, these are the main three topics which we are going to cover today. So, coming to the first one, energy requirements to reach a orbit. So, what is energy required to reach a orbit? So, whenever you are sending an object, it has to overcome the Earth gravitational force, and finally it reaches its destination to a particular orbit. Suppose, let us say this is the center and this is the Earth. Okay, this is Earth and this is the orbit. Let us say this is the orbit. So, a body has to travel from this place on the Earth surface to the orbit. Okay, so here the force of attraction, the force of attraction on the body, suppose if I divide this total distance into some number of parts like 1, this is 0, 2, 3 and 4 segments. At each point, at point 1, the force acting on the body is different, the attraction force acting on the body is different. At 2, at position 2, the force of attraction acting on the body is different due to the Earth gravitational force. And at 4, at 3, at different points, at different altitude, the gravitational attraction experienced by the body is different. It is not actually constant. So, this body has to overcome the attraction force, attraction force by the Earth, and it has to reach the certain altitude. So, whatever the attraction force acting on the body while it is traveling from the Earth surface to the orbit is not actually constant. So, we need to calculate the total force which is acting on the body from Earth surface to reach the orbit. So, that's why we need to calculate the work done. So, the work done required by the body to reach from Earth surface to the orbit of radius r. So, if I take the Earth surface, the radius at the Earth surface is RE. Radius at the Earth surface is RE, and from RE to, I have to move from RE to radius R. So, what is the force acting on the body? That is gravitational force. So, this is a force. I am multiplying the force with the radius, which is actually variable. Radius varies from RE to RE. So, I am integrating this force into distance. That is work done. What is this? This is work done. So, I am integrating this total work done by the body from radius RE, so that is from Earth surface. Radius RE means surface of the Earth to the radius of the orbit. Okay. So, if you go to the force acting, that is nothing but gravitational force, capital G into ME, M by R square into dr. So, now I am going to integrate this gravitational force of attraction acting on the body with respect to the radius from Earth surface to the particular radius. Why I am integrating from RE to R? Because I am sending the object from Earth surface to the particular radius R. That's why I have to integrate from RE to R, not from 0 to R. Okay, we should not integrate from 0 to R. If you consider it is 0, that means you are sending the body from the Earth center. Okay, So that's why we have to integrate from RE to R. So while doing an integration, capital G is constant, mass of the earth is constant, and the mass of the body we are considering, the mass of the body is also constant. The only thing varies is radius. So if we can bring all these terms outside of the integral. We can bring all these terms outside of the integral. Then it will become RE to R, integration RE to R. Just a second. It will become, this will become capital G ME into small m into integration from RE to capital R into 1 by R square dr. Okay, 1 by R square dr. So this is nothing but the energy, the work done by the object to reach the orbit, to reach the orbit. So after integration, this equation will become 1 by R square will become minus 1 by R. So after applying the limits from RE to R, what happens? Capital G, we keep this term aside, and if you integrate, this will become minus 1 by R from RE to R. So if you apply these limits, it will become 1 by RE minus 1 by R. So finally, what is the energy required? So energy required to reach the orbit, is E is equal to capital G ME M into 1 by RE minus 1 by R. So what is R here? Radius of the orbit. It is the target distance, okay, from the earth center. So this is the equation. So with this energy, the body will reach from earth surface to the radius R. Okay. Next, okay, the body will reach from earth surface to the radius. So after that, what do we have to do? So consider, and this is the radius. Now we have provided enough energy for the body to reach from RE to the R. Okay, right. We send the body to the radius of orbit R. After that, this body has to rotate in this orbit with velocity which is equal to orbital velocity. This body has to rotate in this orbit, circular orbit, with velocity which is equal to orbital velocity. So even we have to provide a velocity, V0 for the body to rotate or to stay in the same orbit. So what is that energy? How do we calculate how much energy is required for the body to rotate with V0? So that is nothing but the kinetic energy of the body, m into mass of the body, V0 square divided by 2. So we have to provide additional kinetic energy E0 to the body so that it will rotate in the particular orbit. So initially, previously we have gone through the equation, right? We have derived the energy required to reach the orbit. After that, we have to provide some additional kinetic energy for the orbit. So if you add these two, so this is the energy required to reach the orbit, and this is the kinetic energy required the orbit. So this is nothing but the total energy required for the orbit, total energy required for orbiting the body, total energy required for orbiting the body in the particular orbit. So this is capital G into small m into ME into 1 by RE minus 1 by R plus m V0 square by 2. And here, if you substitute the equation for V0, we know the equation for V0, orbital velocity, under root gm by R. After substituting this, V0 is equal to capital G ME by R. Then this equation will turn to capital G m into ME by 1 by RE minus 1 by 2R. 1 by RE minus 1 by 2R. Right. So if you observe this equation carefully, so what is R here? Radius of the orbit. And I can write this radius of the orbit in terms of radius of the earth. So this is the earth, right? This is the radius of the earth, and this is the radius of the orbit. Okay, so I can write this radius of the orbit is equal to and if I consider this height of the orbit is h, if I consider the height of the orbit is h, then I can write r is equal to, radius of the orbit is equal to re plus h, re plus h, re plus h, right? So I can write radius of the orbit is how much? Re plus h. So I will substitute this re plus h here. Then this equation will become capital G me m by, okay, 2 re into re plus 2h by re plus h. So this equation will be capital G into me m by 2 re into re plus 2h by re plus h. So this is the final total energy required, or total energy to be provided for the object to reach the orbit and to rotate in the orbit with the required orbital velocity. So this is the equation, right? So we have derived the equation, or we have calculated the energy required for a body to rotate in the orbit. Okay, then how much velocity to be provided from the Earth surface so that it reaches the orbit and rotates in the orbit. So now we are going to calculate that total velocity required for orbiting the body, that is Vt. So if I consider I have to provide some kinetic energy for the body which is equal to the total velocity, then the kinetic energy required is mvt square by 2. So if I provide this kinetic energy mvt square by 2, if I consider the total velocity as Vt, and if I provide the energy is mvt square by 2, then it will reaches to the orbit and rotates in the orbit. So I am equating this mvt square by 2 with the total energy equation which we have derived earlier. So equate this both. So if I equate this, half mvt square which is the kinetic energy I have to provide for the body, then here 2 will get cancelled, m will get cancelled, and whatever the square, it will become under root. And finally you will get the equation for velocity, total velocity required to reach the orbit. So then the total velocity required is capital G me into re plus 2h, as it is re plus 2h by re into re plus h, re into re plus h. So this is the equation for total velocity required, for the total velocity to be provided for the body to reach the orbit and rotate in the orbit with orbital velocity. So this is about the energy requirements for the body to reach the orbit and to rotate in the orbit. And this is the graph. Okay, here this is the graph. You can see altitude on the x-axis in kilometers and velocity in kilometers on the y-axis, and you can observe the graphs of total velocity required and orbital velocity. Okay, you know, if you observe the equation of total velocity, the total velocity varies with respect to the radius of the orbit, and the orbital velocity actually decreases with the radius. Orbital velocity decreases with the radius. Or V0 is equal to under root capital G me by r. So here V0 is inversely proportional to the radius of the orbit, and total velocity Vt is directly proportional to the radius of the orbit. So here you can see the variation of this velocity requirements with respect to altitude. So up to some altitude, almost this total velocity and orbital velocity are almost same up to this altitude, around 100, in between 100 to 1000. I can say this is up to 300 kilometers per approximately up to 300 kilometers or some altitude between 100 to 1000. So total velocity and orbital velocity both are almost same. After this, you can observe the increase in total velocity. The total velocity is increasing with altitude and orbital velocity is decreasing with altitude. So this is the variation of total velocity and orbital velocity. So orbital velocity is just the velocity required to rotate in the orbit. That's it. Total velocity means it includes, we have to provide the velocity required to reach the orbit, and also we have to provide orbital velocity. So that's why it is more than the orbital velocity. So this is about the topic energy required to reach a orbit. So coming to the summary of today's topic, we have gone through the energy requirements to reach a orbit. So how much energy is required to send from Earth's surface to the orbit. After that, the total energy required to rotate in the orbit, and we have also gone through the total velocity required to rotate in the orbit. So these are the topics which we have covered today. Thank you.